Hi all. Today we are going to discuss about spectrum analyzer. So, a spectrum analyzer is a device that measures and displays the signal amplitude strength as it varies by frequency within its frequency range of spectrum. The frequency appears on the horizontal x-axis and the amplitude is displayed on the vertical y-axis. It looks like an oscilloscope, and in fact some devices can be function as either oscilloscopes or spectrum analyzers. So what is the importance of spectrum analyzers? So radio frequency signals and wireless communications are today thanks to Wi-Fi, mobile networking and communications, wireless Internet of Things devices, sensors, traditional radio, radar and more. To test and design such circuits and systems, it is useful to see the entire signal spectrum and other factors like spurious signals, noise, modulated signals with etc. Devices like swept spectrum analyzers and vector signal analyzers do not provide such capabilities. Also, they provide only snapshots of the signal in either the frequency or modulation domain, which cannot describe the dynamic and transient nature of modern RF signals. This is where spectrum analyzers are valuable. So, the problems associated with non-real time analysis in the frequency domain can be eliminated by using spectrum analyzer. A spectrum analyzer is a real-time analyzer, which means that it simultaneously displays the amplitude of all the signals in the frequency range of the analyzer. And like wave analyzers provide information about the voltage of energy of a signal as a function of frequency. Unlike wave analyzers, spectrum analyzers provide a graphical display on a CRT. And the problems associated with non-real-time analysis in the frequency domain can be eliminated by using a spectrum analyzer. A spectrum analyzer is a real-time analyzer, which means that it simultaneously displays the amplitude of all the signals in the frequency range of the analyzer. And the real-time or multi-channel analyzer is basically a set of stagger-tuned bandpass filters. Stagger-tuned bandpass filters connected through an electronic scan switch to a CRT. The composite amplitude of the signal within each filter's bandwidth is displayed as a function of the overall frequency range of the filter. Therefore, the frequency range of the instrument is limited by the number of filters and their bandwidth. The electronic switch sequentially connects the filter's output to the CRT. And the spectrum analyzer horizontal deflection is obtained from the scan generator, which has a sawtooth output that is synchronized with the electronic switch. So this picture shows the block diagram of the audio spectrum analyzer. Such analyzers are usually restricted to audio frequency applications and may employ as many as 32 filters. The bandwidth of each filter is generally made very narrow for good resolution. The relationship between a time domain presentation on the CRT of an oscilloscope and a frequency domain presentation on the CRT of a spectrum analyzer is shown in three-dimensional drawing. And it shows in the next figure shows a fundamental frequency f1 and its second harmonic 2f1. An oscilloscope used to display the signal in the time amplitude domain would display only one waveform, the composite of f1 plus 2f1. And the spectrum analyzer used to display the components of the composite signal in the frequency amplitude domain would clearly display the amplitude of both the fundamental frequency f1 and its second harmonic 2f1. And these analyzers are used to obtain a wide variety of information from various kind of signals, including the spectral purity of continuous wave signals, percentage of modulation of amplitude modulated signals, deviation of frequency modulated signals, which is FM, and noise such as impulse and random noise, and filter frequency response. So the three-dimensional relationship between the time, frequency and amplitude is shown in this figure from spectrum analyzer. So this is the test setup to measure the total harmonic distortion of an amplifier. It is consists of audio oscillator and amplifier under test and a distortion analyzer, which is connected to load resistor. So waveform is applied to the amplifier. The output of the amplifier is applied directly to the distortion analyzer, which measures the total harmonic distortion. In the field of microwave communications, in which pulsed oscillators are widely used, spectrum analyzers are an important tool. They also find wide applications in analyzing the performance of AM and FM transmitters. Spectrum analyzers and Fourier analyzers are widely used in applications requiring very low frequencies in the field of biomedical electronics, geological surveying, and oceanography. They are also used in analyzing air and water pollution. Another very important application of spectrum analyzer is the measurement of intermodulation distortion. This phenomenon occurs when two or more signals are applied to the input of a nonlinear circuit, such as an amplifier, particularly a power amplifier. This problem is particularly troublesome in the reproduction of music. If the signals are applied to a completely linear circuit, each passes through the circuit unaffected by the other. However, if there is non-linearity in the circuit, heterodyning of the signals occurs. So, limiting our discussion to two signals, we find that heterodyning occurs because the lower frequency signal tends to modulate the higher frequency signal. So, if F1 and F2 are the fundamental frequency of the input signals, the output spectrum may contain any or all of the frequencies, and it is shown in this figure. So, some of the harmonics of F1 and F2 produced by amplifier nonlinearity, and amplitude modulated waveform produced by intermodulation distortion, which is shown in this figure. So, if the non-linearity of the circuit is significant, the modulation of the higher frequency signal by the lower frequency signal will produce the familiar amplitude modulation waveform. So, the percentage of intermodulation distortion is computed as capital M minus small m and capital M minus small m into 100%, where IMD, the intermodulation distortion, expresses as a percentage, capital M the peak to peak modulated signal, and small m the minimum value of the modulated waveform. So the spectrum analyzer can be used to measure the intermodulation distortion. The frequency of the audio oscillator is generally set to 6 kHz. So using the spectrum analyzer to measure the intermodulation distortion, which is shown in this block diagram. Here the audio oscillator, mixer, attenuator, amplifier under test and spectrum analyzer is present, and the source voltage is 115 volt and with the frequency of 60 Hz. So the spectrum analyzer method is explained here with the help of this intermodulation distortion.